Imagine you solved the hardest problem in the history of physics. Imagine the engineers and the theorists and the experimenters all agreed that it was done, that the warp bubble had been built, or the exotic matter had been confirmed, or some other mechanism had been found that allowed a ship to travel at the speed of light. Not approaching the speed of light, not 99.99% of it, at it. The full 186,000 miles per second, the absolute maximum speed that anything in the universe has ever moved. You solved it, and then someone ran the numbers on where you could actually go, and what it would cost you to get there, and what would be left when you came back. The nearest star beyond our sun is 4.24 light years away. At the speed of light, you would arrive in 4.24 years. That is a journey. A real one. Long enough to require planning, short enough to be imaginable as a human undertaking. You could leave in your 30s and arrive in your late 30s. You could still remember departing. But the nearest star is not the nearest interesting thing. It is just the nearest thing. And the galaxy we live in, the Milky Way, is 100,000 light years across. At the speed of light, crossing it from one end to the other takes 100,000 years. The nearest large galaxy, Andromeda, is 2.537 million light years away. At the speed of light, you arrive in 2.537 million years. The nearest significant galaxy cluster is tens of millions of light years away. The observable universe extends 46 billion light years in every direction. At the speed of light, the universe is still impossibly, almost insultingly large. And that is before you understand what happens to time when you travel at the speed of light. What happens to the world you left behind? What happens to your ability to come home, to communicate, to feel that you belong to the same civilization that launched you? What happens to the idea of a mission that starts somewhere and ends somewhere and means something to the people on both ends? Tonight we are going to follow the speed of light not as a goal to be celebrated, but as a limit that, even if reached, still does not solve the problem. A limit that fails not at the engineering level, not at the energy level, not at the physics level of getting there, but at the human level. At the level of what exploration and civilization and return and belonging actually mean when the mathematics of space-time is taken seriously at its extremes. We will look at what the galaxy actually looks like if you are travelling at light speed. We will look at what really happens to time when you push it to the relativistic limit. We will look at why going somewhere and coming back is a trap that light speed cannot escape. We will look at why a civilization using light speed ships still cannot talk to itself across meaningful distances. We will look at the cosmic event horizon, the boundary the universe has drawn around what is reachable at any speed, and how that boundary is shrinking. And we will look at what all of this tells us about what fast enough would actually require, if the goal is a civilization that can meaningfully inhabit the cosmos. If this is the kind of mission briefing you want more of, subscribe and stay with the crew. Strap in, we begin. But there is a detail about the speed of light that changes the shape of everything that follows. Not about the energy needed to reach it, about what it does to time, and what that does to everything else. A detail so strange that it takes a while to sit with before it resolves from curiosity into consequence. The first thing to understand is the size of the galaxy, not as a number to be read and absorbed in passing, as a structure, as an actual physical environment in which any interstellar civilization would have to function, as the container in which all of human exploration and all of human ambition would have to operate if we ever became genuinely spacefaring in any meaningful sense. The Milky Way is a barred spiral galaxy. It has a bright, dense central bulge packed with older stars, a bar of stars cutting through the centre, and 4 primary spiral arms curling outward from that bar, each one thousands of light years wide and tens of thousands of light years long. It is roughly 100,000 light years in diameter, and perhaps a few thousand light years thick through most of its disk, thickening toward the central bulge. The solar system sits about 26,000 light years from the galactic centre, in a modest spiral spur called the Orion Arm, a minor structural feature between 2 of the larger arms. 100,000 light years in diameter. At the speed of light, crossing the Milky Way from one edge to the other takes 100,000 years. Let that number find its footing before we move past it. The entirety of recorded human civilization spans approximately 10,000 years. From the first permanent cities of Mesopotamia and the Indus Valley, from the invention of writing and the wheel and organized agriculture, from the first kingdoms and the first calendars and the first mathematical systems, all the way to this moment, All of it together takes up a window of time 10 times smaller than the light crossing time of our own galaxy. Anatomically, modern humans have existed for roughly 300,000 years. The non-avian dinosaurs went extinct 66 million years ago. The solar system itself is 4.6 billion years old. 100,000 years is a long time by any measure a human body can intuitively process. A ship travelling at the speed of light from one side of the Milky Way to the other would take 100,000 years to complete the crossing. Every person aboard, if there were people aboard, would be long dead. Their children would be long dead. Their children's children would be long dead. Every generation that descended from the original crew would be long dead, and many of those generations after them as well. The civilization that launched the ship would have transformed, probably multiple times, into something unrecognizable to the people who gave the mission its orders. And the galaxy is just our galaxy. The Andromeda Galaxy, our nearest large neighbour, is approximately 2.537 million light-years away. At the speed of light, a ship launched today toward Andromeda would arrive in 2.537 million years. The civilization that receives the ship, if it still exists as a recognizable entity, would have no meaningful cultural or institutional connection to the civilization that launched it. 2.537 million years is roughly the same amount of time that separates modern humans from our ancestor Homo habilis, one of the earliest species to use stone tools. The gap between the launching civilization and the arriving civilization would be comparable to the evolutionary distance between us and a species that had not yet learned to shape rocks. The return signal from a probe that reached Andromeda and immediately transmitted a simple greeting back to Earth would arrive here 5.074 million years after the probe was launched. 5 million years is approximately the time that separates humans from our last common ancestor with chimpanzees. The people who sent the message and the people who received it would not, in any biological or cultural sense, be the same species. The Virgo cluster, the nearest large cluster of galaxies, sits about 53 million light-years away. A round-trip signal at light speed would take 106 million years. That is longer than the entire reign of the non-avian dinosaurs. The Cretaceous period, the final chapter of dinosaur dominance, lasted from about 145 million years ago to 66 million years ago, a span of 79 million years. A signal from the Virgo cluster and back takes longer than that. The observable universe extends 46 billion light-years in every direction. A message to the farthest observable galaxies and back would require 92 billion years, nearly 7 times the current age of the universe. At the speed of light, the universe is still impossibly large for any coherent civilization to meaningfully span. This is not a minor technical limitation waiting to be overcome by slightly better engineering. It is a structural feature of the universe. The distances are not large the way the distance across an ocean is large, a challenge that requires effort but that can be crossed in a manageable time by a capable civilization. They are large in a different way, in a way that makes the concept of a journey to a specific destination and a return home, bringing knowledge and experience back to the civilization that launched the mission, cease to function as a meaningful description of what is happening. Now add to this one more layer of the galactic picture that is easy to state and difficult to absorb. The Milky Way contains between 200 and 400 billion stars. Even within the galaxy, the distribution of those stars is not uniform. They cluster in the spiral arms, thin out in the gaps, concentrate in the central bulge. Stars in different regions of the galaxy orbit the center at different velocities, so the relative positions of stars change over millions of years. The Sun completes one orbit of the galactic center in roughly 225 million years, a period sometimes called the cosmic year. Other stars at different radii orbit at different rates. A civilization that wanted to settle throughout the Milky Way and maintain any kind of navigable map of where its settlements were would need to constantly update that map, because the positions of all the relevant stars are slowly shifting relative to each other. Not on any human timescale, but on the timescale of a civilization that was genuinely attempting to operate across the galaxy, the drift becomes relevant. The galaxy is not a fixed address. It is a slowly rotating, slowly evolving structure. Navigating within it at light speed, over the timescales involved, requires knowing not just where things are now, but where they will be when the light speed ship arrives. And there is a feature of the universe beyond the galaxy that makes even the intragalactic picture look manageable by comparison, because the universe is not static. It has been expanding since the Big Bang, and the expansion itself has consequences for what is reachable even at the speed of light. The radio signals we have been broadcasting since the dawn of radio technology, the earliest of which left Earth around 1900, have now travelled roughly 124 light-years in every direction. That is the radius of what astronomers sometimes call our radio bubble. Everything within that sphere has, in principle, had the opportunity to receive some of our transmissions. That bubble contains several thousand stars, potentially thousands of planets, and we have received nothing in response. But 124 light-years is 0.12% of the diameter of the Milky Way. Our signals have reached a vanishingly small fraction of our own galaxy. The vast majority of stars in the Milky Way have never had any opportunity to detect us. Our nearest stellar neighbour did not receive our first radio transmissions until 1904. The galactic centre will not receive them until approximately the year 27,900. Stars on the far side of the galaxy will not receive them until the year 101,900. This is the reality of communication at light speed across galactic distances. Not slow, not delayed, but delayed so severely and so asymmetrically that the relationship between sender and receiver becomes essentially severed by the time any signal arrives. The universe is telling us something with these numbers. Not that light speed is too slow for travel. That light speed is too slow for coherent civilization at any scale, larger than a very small cluster of nearby stars. And that even within that small cluster, the timescales for meaningful exchange are measured in years and decades, which is already challenging for institutions and cultures that evolved to function on timescales of days and years. Stretching to centuries and millennia and millions of years does not solve the challenge. It eliminates the possibility of meeting it at all. Here is another way to make the scale tangible, not through analogies or scaled models, but through the actual physics of what we have already done. The earliest deliberate radio transmissions from Earth, signals strong enough and directional enough to have any chance of being detected by a receiver beyond our planet, date to roughly 1900. Those signals have been travelling outward at the speed of light for roughly 124 years. They have now reached all stars within about 124 light-years of Earth. Within that sphere, astronomers estimate there are roughly 15,000 stars. If even a small fraction of those have inhabited worlds with civilizations advanced enough to be listening, some of them might have received our earliest transmissions decades ago. But 124 light-years is 1/10 of 1% of the galactic diameter. The radio bubble contains roughly 15,000 out of the 200 to 400 billion stars in the Milky Way. It is a vanishingly small sample. The vast majority of stars in our own galaxy have received no signal from us. A civilization 1,000 light-years away could not hear from us until the year 3024 at the earliest, and their response could not reach us before the year 4024. A civilization at the galactic centre, 26,000 light-years away, will not receive our first radio transmissions for another 25,876 years. We have been broadcasting for about 124 years and heard nothing back. But for almost any interesting destination in the galaxy, the return signal could not possibly have arrived yet. The silence of our radio telescopes is not evidence that no one is out there. It is evidence of how large the galaxy is. The stars within our radio bubble are also the stars we could reach most quickly at light speed. Stars 50 to 124 light-years away. These are the nearby stars, the first destinations any civilization attempting to bootstrap interstellar capability might target. Astronomers have identified hundreds of potentially habitable exoplanets within a few hundred light-years of Earth. Some have the right size and orbital distance from their star. Some have atmospheres detected remotely. We have candidate worlds. We do not know if any of them are inhabited, but we know they are there. Rocky worlds at the right distance from stable stars. The first generation of destinations, the first questions the galaxy is ready to let us ask. And the problem is not reaching them at light speed. A journey to a star 50 light-years away takes 50 years at light speed. That is manageable, barely, in human institutional terms. The problem is what comes after arrival. Whether the civilization that sent the mission still exists in a form that recognizes the returning explorer and values what the explorer found. But the problem of scale, enormous as it is not the strangest part of travelling at light speed. The strangest part is what happens to time. not the time delay of communication, not the time required for the journey as experienced on Earth. What happens to the time experienced by the traveller themselves? Because Einstein's relativity is very specific about this. And what it says is more radical than most people expect when they first encounter it. Special relativity predicts that moving objects experience time at a slower rate than stationary ones. This is called time dilation. It is not a perception or an approximation. It is a physical reality that has been measured directly, confirmed repeatedly, and built into the design of every GPS satellite currently in orbit. The clocks on GPS satellites run at a slightly different rate than clocks on the ground, and if the satellite systems did not correct for this, the positioning errors would accumulate at roughly 11 kilometers per day, rendering the entire system useless within hours. The time dilation effect is governed by a mathematical expression called the Lorentz factor. The Lorentz factor takes the ratio of your velocity to the speed of light as its input, and produces the ratio of your time to external time as its output. The relationship is not linear, it is not even simply exponential. It behaves in a specific way that becomes more and more extreme as you approach the speed of light. At 10% of light speed, the dilation is small. Your clock runs at about 99.5% of the rate of a stationary clock. Barely noticeable. At 50% of light speed, your clock runs at about 87% of the stationary rate. For every year on Earth, you experience about 10.5 months. At 90% of light speed, your clock runs at about 44% of the stationary rate. For every Earth year, you experience about 5.5 months. At 99% of light speed, your clock runs at about 14% of the stationary rate. For every Earth year, you experience about 7 weeks. At 99.9% of light speed, your clock runs at about 4.5% of the stationary rate. For every Earth year, you experience about 16 days. At 99.99% of light speed, about 1.4%. For every Earth year, you experience about 5 days. At 99.9999% of light speed, for every Earth year, you experience about 7 hours. Follow this curve to its mathematical limit. At exactly the speed of light, the Lorentz factor becomes infinite. Your clock, if you were travelling at exactly the speed of light, would stop entirely. Zero. No time passing, no heartbeats, no thoughts, no aging, no experience of any kind between departure and arrival. A photon of light, if it could be said to have any experience at all, does not experience its journey. It exists at the moment of its emission and at the moment of its absorption, simultaneously, with no subjective interval between them. The billions of years a photon might spend crossing the universe, the entire lifespan of galaxies through which it passes, amount to literally nothing from the photon's reference frame. It is created and it is absorbed. That is all. This is what travelling at the speed of light means for the traveller. Not a long, difficult, isolating journey, not centuries of endurance and adaptation, not the slow drift of interstellar dark, nothing at all, an instantaneous transition from departure to arrival. 0 seconds, 0 subjective experience, you press the button and you are there. That sounds, at first encounter, like the ideal solution to every problem of interstellar travel. No crew aging problem, no multi-generational ship problem, no psychological cost of isolation, no need to keep a crew mentally healthy for decades. You leave, you arrive, and from your perspective, no time has intervened. The journey is not even a journey in any experiential sense. It is a translation. But here is the cost, and it is not a cost that can be engineered away. It is built into the same mathematics that creates the zero-time experience for the traveller. If no time passes for you during the journey, then all the time passes for everyone else. Every second that passes at your departure point, every year that passes on Earth, passes in full, without any discount or compression, while you are in transit. The universe does not give you time dilation for free. It takes the time you saved and gives it to everything you left behind. You gain time dilation. Everything else gains the full uncollapsed interval. A trip to Proxima Centauri at light speed takes 4.24 years from Earth's perspective and 0 seconds from your perspective. A trip to the galactic centre takes 26,000 years from Earth's perspective and 0 seconds from yours. A trip across the Milky Way takes 100,000 years from Earth's perspective and 0 seconds from yours. For you, the journey is a moment. For everything you left behind, the full travel time passes without interruption, without pause, without any compression or shortcut of any kind. Think about what this means for a human being. You board a light-speed ship, you say goodbye to your family, your friends, your colleagues, your city, your civilization, you travel to the galactic center. From your subjective perspective, the journey is instantaneous. You arrive, you look around, you spend some time at the destination, you board the ship again, and travel home. From your perspective, the entire mission is brief. You feel as though you left this morning and are returning tomorrow. But 52,000 years have passed on Earth. Not 52,000 years of slow drift that someone might have waited through. 52,000 years of history that actually happened, in full, without you. Every person you said goodbye to has been dead for most of those 52,000 years. Their children have been dead for most of them. Their children's children. Every generation of every family you knew, gone. The language you spoke has changed beyond recognition, or has become extinct and been replaced. The institutions that supported the mission, the government agencies and research universities, and private organizations that built your ship and gave your mission its purpose, have been gone for tens of thousands of years. The civilization that launched you may be a dim historical memory, the way the Bronze Age kingdoms of Mesopotamia are a dim historical memory to us. Your ship lands, you step out. You have been gone from Earth's perspective for 52,000 years. There is no home to return to, not in any sense that the word home carries. The planet is still there. The sun is still burning, still in the middle of its lifespan. The Milky Way is still turning. But the civilization, the culture, the human context that made the journey meaningful, the specific people and institutions and shared understanding that you left, are as gone as the world of ancient Egypt is gone from our perspective. Present in records, perhaps. Present as archaeology. Not present as a living community that remembers you and was waiting for your return. This is the twin paradox, pushed to its logical extreme. In the standard twin paradox, one twin travels at high speed and the other stays home. The travelling twin returns younger. The age difference is real. The discrepancy grows with speed. At light speed, the discrepancy is not a quantitative difference, but a qualitative one. The travelling twin experiences zero time. The stationary twin experiences the full travel time. There is no meeting in the middle. There is only the complete divergence of two timelines that share a departure point, and then separate in the most extreme way that physics allows. And it does not even require going to the galactic centre for this problem to become severe. Going to the nearest star and coming back at exactly light speed means Earth experiences 8.48 years while you experience 0. Not catastrophic. Your friends and family are still there. The world is still recognizable. But going to a star 100 light-years away and coming back means Earth experiences 200 years. Going to a star 500 light-years away and coming back means Earth experiences 1,000 years. Going to any of the interesting destinations, the dense star-forming regions, the exotic stellar remnants, the most promising planetary systems identified by astronomers as potentially habitable, most of which are hundreds or thousands of light-years away, means a return to a world that has changed beyond institutional memory of the departure. The physics that makes light speed attractive for the traveller, the zero subjective journey time, is the same physics that makes it catastrophic for the civilization. You cannot have both. The time dilation that gives the crew an instant crossing gives the home planet the full, uncollapsed weight. The twin paradox, taken to its extreme, reveals something about the nature of human identity that rarely gets said explicitly. We are not just biological entities with memories and skills and knowledge. We are also nodes in social networks. We are defined partly by our relationships, our institutional affiliations, our cultural contexts, our shared languages and references and histories. These things are not merely attachments to a self that could exist independently of them. They are partly constitutive of the self. Remove them, and what remains is a different kind of entity, one that carries the memories of belonging without the actual belonging. A crew member who departs Earth at light speed for the galactic centre, experiencing 0 seconds in transit and returning after 52,000 Earth years, does not merely return to a changed world. They return as a kind of orphan. Not in the familiar sense of a person whose parents died, in a more complete sense, an orphan of their civilization, of their language, of their culture, of every context that gave the specific texture and meaning to their specific life. The people who knew them are gone not just by a generation but by hundreds of generations. The world they grew up in is not history. It is prehistory. What does exploration mean for this person? What does the knowledge they gathered on the journey mean to them if there is no living community that shares the framework within which that knowledge was meaningful? If the scientific community that sought the knowledge has transformed beyond recognition, if the questions that motivated the mission have been answered differently or abandoned entirely, if the very civilization that defined what counted as interesting or valuable has become something the returning explorer cannot recognize as theirs. The mission was supposed to generate knowledge. The knowledge was supposed to flow back into the civilization, but the civilization is gone. The knowledge has nowhere to flow. The explorer carries it alone, inside a context that no longer exists outside their own memory. This is not a problem with a technical solution. It is not something that better equipment or better training or better mission planning can address. It is a consequence of the mathematics. The physics that creates the zero-time experience for the traveller also creates the 52,000-year gap for the civilization. You cannot have one without the other. They are the same relativistic effect, described from two different reference frames. To travel at light speed is to accept a trade. Your subjective journey time drops towards zero. Your connection to everything you left behind drops towards zero with it. The universe gives you an instantaneous crossing and takes, in exchange, the world you are crossing to return to. That trade might be worth making in some circumstances, if the knowledge to be gained is sufficiently important, if the explorer is sufficiently willing to accept the cost of returning as a stranger, if the civilization is sufficiently long-lived and stable that 52,000 years of elapsed time still leaves something recognizable and welcoming on the other end. But it is a trade, and it is a severe one, and it is worth naming clearly, rather than treating light speed as simply a fast way to get somewhere and come back, because it is not. It is a mechanism for arriving at your destination with zero subjective journey time, and returning to a world that has aged by the full travel time. It is the opposite of what exploration, in the human sense, has always meant. The great explorers of human history were changed by their journeys. They came back different from how they left. But they came back to a world that had also changed in a proportionate way over the months or years of their absence. The changes were commensurate. The world moved on, they moved on, they could still find each other, they could still communicate. They could still share what they had learned. At light speed, the changes are not commensurate. The traveller changes not at all subjectively. The world changes enormously. The asymmetry is absolute. And it is not the kind of asymmetry that human relationships, human institutions, or human civilizations have ever been designed to accommodate. And this leads directly to the round-trip problem, which is in some ways the heart of everything. When we talk about exploration, about interstellar missions, about the aspiration to visit other stars and other worlds, we are almost always imagining a round trip, a journey with a departure and an arrival and a return. Something that begins here, goes there, and comes back. A mission with two endpoints and a continuous thread connecting them. The explorer leaves. The explorer discovers something. The explorer comes home and tells us what they found. The knowledge circulates back into the civilization that sent the expedition. The civilization is changed by what it learns. This is the model of exploration that every human civilization has ever operated on. Magellan's expedition left Spain, sailed around the world and came back to Spain. Lewis and Clark left St. Louis, crossed the continent to the Pacific Ocean, and returned to St. Louis. The Apollo astronauts left Earth, travelled to the Moon, and returned to Earth. In every case, the knowledge generated by the journey returned to the civilization that launched it, within a time frame short enough that the same civilization still existed to receive it. The same people, or at least the same generation of people who sent the expedition, could benefit from what it learned. At light speed, this model collapses for any destination beyond a few dozen light years. Consider the distances involved. A light-speed round trip to Proxima Centauri takes 8.48 years as experienced on Earth. The mission could be planned, launched, and received within a single decade. A person who was 40 when the probe launched could be 48 when the return data arrived. This is manageable. This is within the range of institutional and human continuity. The people who funded the mission are still the people who receive its results. A light-speed round trip to a star 50 light-years away takes 100 years as experienced on Earth. The people who launched the mission are almost certainly gone when it returns, but the institutions that funded it might still exist. the civilization is still recognizably the same civilization. The technology that was state-of-the-art at departure might be obsolete at return, but the data is still useful. This is stretched, but arguable. A light-speed round trip to a star 500 light-years away takes 1,000 years on Earth. The institution that funded the mission has had 1,000 years to evolve, reorganize, be destroyed, be replaced, be forgotten, and perhaps be replaced again. The language in which the mission's objectives were written may no longer be spoken. The scientific questions the mission was designed to answer may have been addressed by other means, or may have become irrelevant as the field moved on. The civilization that receives the data is 1,000 years removed from the civilization that sought it. This is not a round trip in any meaningful sense. It is two separate civilizations, connected only by the historical record of a shared earlier state. A light-speed round trip to the galactic center takes 52,000 years on Earth. The human species itself has only existed in its anatomically modern form for about 300,000 years. A round trip to the galactic center at light speed covers roughly 1/6 of the entire duration of our species' existence. The civilization that receives the return data has no institutional, cultural, linguistic, or likely even biological continuity with the civilization that launched the mission. A light-speed round trip to Andromeda takes 5.074 million years on Earth. This is not a round trip for any civilization in any meaningful sense. It is a message in a bottle, thrown into the sea by one species and found by whatever species happens to be living at that location millions of years later. The round-trip structure of exploration, the thing that makes exploration exploration rather than simply sending things away and never hearing from them again, requires that the journey be short enough for the same civilization to maintain continuity from departure to return. It requires institutional memory. It requires that the people or the institutions that wanted to know something still exist and still care about the answer when it arrives. Lightspeed cannot satisfy this requirement for any destination beyond a very small neighborhood of nearby stars. And within that small neighborhood, the interesting science, the things that would justify the enormous cost and difficulty of an interstellar mission, is limited. The truly interesting destinations, the star-forming regions, the black hole at the galactic center, the most promising exoplanets, the dense clusters where interactions between stars create unusual phenomena, most of those are hundreds or thousands of light-years away, deep in the territory where light-speed round trips take longer than any civilization can maintain coherent purpose. The round-trip trap does not just affect human missions. It affects any signal, any information, any exchange between civilizations separated by those distances. A civilization that detects our radio signals, which left Earth around 1900, will not receive them until they have travelled for the light travel time to that civilization. If that civilization is 1,000 light-years away, they will receive our signals in approximately the year 2900. If they respond immediately, their response arrives here no earlier than the year 3900. A single exchange of messages, one question and one answer, takes 2,000 years. This is not a fast pen-pal relationship. This is an exchange that spans longer than all of recorded Western history. Both civilizations must maintain consistent interest, consistent technology, and consistent institutional purpose for 2,000 years without interruption, just to complete a single round-trip exchange of information. And 2,000 years is for a neighbor only 1,000 light-years away. For a neighbor 10,000 light-years away, a single exchange takes 20,000 years. For a neighbor on the far side of the galaxy, 100,000 years. The Milky Way, even within itself, is structured in a way that makes meaningful real-time dialogue between its different regions essentially impossible at light speed. This is the round-trip trap. It is not just a problem of travel. It is a problem of any relationship, any exchange, any shared purpose between parties separated by interstellar distances. Light speed is fast enough to eventually get there. It is not fast enough to maintain any continuous relationship between departure and return. And there is a harder version of this problem that we have not yet stated explicitly. Even within the small neighborhood of nearby stars where light-speed round trips are short enough to be arguably meaningful, the universe is not cooperating in the way we might hope. Because even the nearest stars are not fixed destinations, they are moving. Stars in the Milky Way orbit the galactic center, each at a slightly different velocity depending on its distance from the center and its position in the galaxy's gravitational field. Nearby stars are also moving relative to each other due to their individual velocities through space, velocities that are small on galactic scales but significant when you're trying to aim a ship that will not arrive for years or decades. Proxima Centauri is currently moving relative to the Sun at about 14 miles per second. By the time a light-speed ship launched today arrived at Proxima's current position, Proxima would have moved about 59 astronomical units from where the ship was aimed. The ship would need to correct for this, which means the destination of any interstellar mission is a predicted future position, not a present one. This is manageable for nearby stars and short travel times. It becomes progressively more complex for distant stars and long travel times. At light speed, the targeting problem for a destination 1,000 light-years away means predicting, with sufficient accuracy, where a specific star will be in 1,000 years. Stars move in complicated gravitational fields. The precision required grows with the distance and the travel time. This does not make light-speed travel impossible, but it adds another layer of complexity to a problem that is already challenging in every other dimension. There is a specific thought experiment that makes the round-trip problem vivid in a way that abstractions sometimes fail to achieve. Imagine a scientist, a brilliant researcher at the peak of their career, 35 years old, with 30 years of productive scientific work ahead of them if they stay on Earth. They are offered the mission of a lifetime: travel at light speed to a star system 50 light-years away, observe a planetary system that shows strong signs of harboring complex life and return with the data. From their perspective, the round trip takes approximately 0 time. They leave, they arrive, they observe, they return. 0 subjective seconds. From Earth's perspective, the mission takes 100 years. Their colleague who stayed home, also 35 at departure, is now 135 years old if they survived that long. Their children are elderly. Their grandchildren are middle-aged. Their institution has had 100 years of leadership changes, funding cycles, scientific revolutions, and paradigm shifts. The scientist returns with extraordinary data about life on another world, the most important data in the history of science. But the scientific community that wanted that data has had 100 years to evolve. The specific questions the mission was designed to answer may have been addressed, partially, by other telescopes that didn't exist when the mission launched. The frameworks within which the data makes sense have shifted. The people who most urgently needed the information are retired or dead. The scientist must spend years, perhaps decades, simply catching up with what has changed in their field, learning the new languages of current scientific discourse, understanding why certain questions that seemed central in their time are now considered settled, or irrelevant, or framed differently. Before they can even communicate what they found, they must understand the current context well enough to translate their findings into it. This is not an extreme scenario. This is a 100-year round trip, a relatively modest interstellar mission at light speed. The disconnection is already severe, and the scientist in this scenario is fortunate compared to those who travel farther. A 500 light-year round trip means 1,000 Earth years. A 1,000 light-year round trip means 2,000 Earth years. The institution, the culture, the scientific framework, the language, the civilization itself have had 1,000 or 2,000 years to transform. The knowledge the explorer carried so carefully, tended so meticulously through a subjectively brief mission, may arrive in a context so changed that it cannot be received. Not because the data is wrong, because there is no longer a community with the right context to understand what the data means, why it matters, and what to do with it. And this problem does not apply only to scientific missions. It applies to every form of purposeful interstellar travel: a colonization mission, a diplomatic expedition, a supply convoy, a communication relay. Every mission that departs with a purpose defined by the civilization that launched it, and that must deliver on that purpose to a civilization that exists when it arrives, faces the round-trip trap. The purpose of a colonization mission is to establish a settlement that remains in contact with and in relationship to the home civilization. But if the mission takes 200 years from Earth's perspective, the home civilization has changed substantially by the time the colony is established and begins sending back messages. The colony was founded by people trained in one culture and governed by one set of institutions, but it is communicating with a culture and set of institutions that have evolved significantly in the interim. The colony and the home world are already growing apart before the first colonists have children. The purpose of a diplomatic expedition is to establish or maintain relationships between civilizations, but diplomacy requires common frameworks of understanding, shared references, negotiating positions that make sense within a shared context. A diplomatic mission that takes 500 years from Earth's perspective returns to find that the diplomatic context that motivated the mission has transformed entirely. The civilizations that were negotiating have evolved. The issues that were at stake have changed. The agreements the mission was supposed to broker may be irrelevant to the current relationship between the parties. Every purpose that a lightspeed mission might serve requires a continuity between departure and return that the time dilation mathematics systematically undermines for any destination beyond a very small neighborhood of nearby stars. Now consider what it would mean for a civilization not just to travel at light speed, but to use light-speed travel to build something coherent across the galaxy. Not just individual missions, but a network, a connected set of worlds that shared knowledge and culture and governance and whatever else civilizations share that makes them civilizations, rather than simply adjacent populations. Consider what civilization actually requires. A civilization is not merely a collection of individuals located in the same physical space. It is a system for sharing information, resolving disputes, coordinating behavior, and maintaining enough cultural coherence that its members recognize each other as members of the same civilization. It requires communication that is fast enough to be useful. It requires governance that can respond to events within the lifespan of the people affected by those events. It requires culture and language and knowledge that circulate quickly enough to remain shared rather than diverging into irreconcilable variants. On Earth, all of these requirements are met, sometimes barely, sometimes with great difficulty, but met. Modern global communication allows any 2 points on Earth to exchange information within fractions of a second. That is fast enough for nearly any human institutional purpose. A law passed in one country can be known and responded to by every other country within days. A scientific discovery published in one part of the world is accessible to researchers everywhere within hours. The world is not perfectly coordinated, obviously, but the speed of communication is not the limiting factor. Human institutions have enough bandwidth and low enough latency to function at planetary scale. Stretch that communication system to interstellar distances at light speed, and it stops functioning. A civilization with settlements spread across 100 light-years has a maximum communication delay of 100 years between its most distant members, not 100 seconds, not 100 minutes, 100 years. Decisions made at one end of the civilization take 100 years to even reach the other end. A response to those decisions takes another 100 years to return. A single round-trip policy exchange takes 200 years, assuming both parties respond immediately upon receipt without deliberating. No human governance system has ever successfully operated with 200-year round-trip communication delays. No human culture has ever successfully maintained shared identity and coherence with 100-year delays between any 2 points. The Roman Empire, which controlled a territory perhaps 3,000 miles across, with communication delays of weeks to months, struggled enormously with coherence and governance. The delays were a significant factor in the fragmentation and eventual collapse of central authority. And that was with delays of weeks, not years, not decades. A civilization spanning 1,000 light-years would have communication delays of up to 1,000 years between its most distant members. A round-trip exchange takes up to 2,000 years. This is not a civilization. It is a collection of isolated populations that happen to have descended from a common ancestor. Each one has had centuries to develop its own language, its own culture, its own political systems, its own scientific frameworks, its own conception of itself and its relationship to the wider cosmos. By the time a message arrives from one branch of the civilization to another, it is, in every meaningful sense, a message from a foreign civilization to another foreign civilization. The shared ancestry is a historical fact, the way the shared ancestry of all living humans is a historical fact, but it is not a living relationship. The Roman coordination problem that ended an empire would look trivial by comparison. To make this concrete, consider what governance looks like at interstellar distances with light-speed communication. Imagine a law is passed by the central government of a light-speed civilization at some central world. The law is transmitted to all member worlds at the speed of light. A member world 500 light-years away receives the law 500 years after it was enacted. The conditions that motivated the law have changed. possibly beyond recognition, in those 500 years. The world's population has never known a time without this law existing as a historical fact, but they are receiving it for the first time. They might respond with questions, with objections, with requests for clarification. Those responses take 500 years to return. By the time the central government receives those responses, 1,000 years have passed since the original law was enacted. The government that enacted the law may not exist anymore. The leaders who wrote it are dead. The political coalition that supported it has dissolved and reformed multiple times. The original motivation for the law has receded into historical context. The responses from the distant world are being received by an institution that no longer has the context to understand why it sent the original message in the first place. This is not governance, it is archaeological correspondence. Messages from the past to the future, received out of context, responded to out of context, in a chain that can never catch up with itself, because the universe insists that information travel at a speed that cannot keep pace with the changes that information is trying to coordinate. And the problem is not just governance, it is science. A scientific discovery made on one world of a light-speed civilization takes hundreds or thousands of years to reach the rest of the civilization. By the time it arrives, the destination worlds have either independently made the same discovery, made a different discovery that supersedes it, or have moved in a direction that makes the transmitted discovery irrelevant or incomprehensible within the scientific framework they have since developed. Science advances fastest through rapid iteration, through the rapid exchange of results, hypotheses, confirmations, and refutations. At light-speed communication delays, the scientific communities of different worlds would diverge rather than converge, each developing its own frameworks and languages and paradigms, each making sense only in the local context, each increasingly alien to the frameworks of the other worlds. A civilization cannot share knowledge across interstellar distances at light speed in any way that maintains the coherence and productivity of a scientific community. It can only create a series of parallel, isolated scientific communities that occasionally receive postcards from each other's distant past. And culture, the shared stories and values and aesthetic sensibilities that make a civilization recognizable to itself, diverges even faster than governance or science. Human cultures that have been separated for a few hundred years produce languages so different they become mutually unintelligible. A few thousand years of separation produces populations that are essentially foreign to each other in culture, religion, values, and social organization. A civilization whose worlds are separated by centuries of communication delay would not, after a few thousand years, share a meaningful common culture. It would share a common origin story, the way all of humanity shares an origin story rooted in Africa. But origin stories are not the same thing as living shared culture. The light-speed communication limit does not merely slow down the exchange of information between worlds. It structurally prevents the kind of information exchange that civilization requires to function as civilization. It guarantees that any collection of worlds more than a few light-years apart will diverge, culturally and institutionally and scientifically, faster than any common framework can be maintained across the distances and delays involved. Lightspeed travel builds worlds that depart together and arrive separately. Each one a distinct civilization within a generation or two of founding, each one isolated from all the others by delays too severe for any shared governance or shared culture to bridge. Consider what this means for science specifically. Because science is perhaps the clearest case where the communication speed problem produces visible and concrete consequences. Modern science advances through rapid iteration. A researcher publishes a result. Other researchers replicate it, challenge it, extend it, or find exceptions to it. The author responds. The community converges on a consensus or identifies a productive disagreement. New experiments are designed based on the consensus. New results emerge. The cycle continues. At its best, this cycle operates on timescales of months and years. Major paradigm shifts take decades. But the key feature is the rapidity and bidirectionality of the exchange. Science is not a series of monologues, it is a conversation. The conversation requires participants who can respond to each other within relevant timescales. A researcher who publishes a result and must wait 1,000 years for the community's response is not a participant in a conversation. They are a broadcaster into the void. The people who read their work 1,000 years later are not responding to what the original researcher said. They are archaeologists interpreting a historical document in light of 1,000 years of subsequent development. A light-speed civilization spanning the galaxy has no scientific community. It has a collection of isolated scientific cultures, each developing independently, each building its own frameworks and terminologies and paradigms, each sending occasional transmissions to the others that arrive centuries or millennia after they were sent, in contexts that have since changed so completely that the transmitted work requires intensive historical scholarship to interpret. Two scientific communities separated by 500 light-years, exchanging papers at light speed, would have a communication lag of 500 years per message. A research program that builds on a previous result would, at minimum, have to wait 500 years for confirmation of that result before taking the next step. In 500 years, the field will have moved in many other directions simultaneously, each direction building on whatever was locally available without waiting for the distant community's contribution. By the time the confirmation arrives, it may no longer be relevant to what the local community is working on, because the local community has been building its own framework for 500 years without the input. Science at light-speed interstellar distances does not converge, it diverges. Each world's scientific community becomes increasingly distinct from every other world's community over time, as each builds on its own local inputs, and the inputs from other worlds arrive too late to shape the direction of inquiry. The isolation is not total. Knowledge does cross the distances, but it crosses too slowly to maintain the kind of ongoing dialogue that produces convergent scientific progress. The same is true of mathematics, of philosophy, of art, of religion, of political theory, of every field of human inquiry that builds on itself over time and depends on cross-fertilization with other practitioners to develop productively. A civilization of isolated worlds communicating at light speed across distances of hundreds or thousands of light-years is not a single intellectual tradition. It is a branching tree of traditions, each branch growing in its own direction, each receiving influences from the others only as delayed echoes of past states, each becoming increasingly foreign to the others over centuries and millennia of independent development. There is a deep irony in this. The desire for interstellar exploration is, at its core, a desire for connection, a desire to know what is out there, to find other worlds, to find perhaps other civilizations, to learn from them and share with them and feel, however briefly, that the universe is not empty, that we are not alone. But light speed, even if achieved, does not deliver connection. It delivers arrival, which is not the same thing. Arriving somewhere does not create a relationship if the communication delay prevents any meaningful ongoing exchange. Arriving somewhere does not generate knowledge that serves the civilization that sought it, if the civilization has changed so much during the journey that the knowledge no longer fits the questions it was meant to answer. Light speed gives you physical presence at a distant location. It does not give you membership in a community spanning that distance. It does not give you participation in a shared intellectual tradition that spans that distance. It does not give you a civilization that is coherent and recognizable, and that functions as a civilization rather than as a collection of isolated points scattered across a volume of space too large for any signal to traverse in any practically useful time. Connection requires not just reaching, but remaining connected after reaching, and remaining connected requires communication that is fast enough to sustain ongoing relationship. Light speed is not fast enough to sustain ongoing relationship at galactic distances, not even close. And then there is the expanding universe. The galaxy is large. Communication at light speed is impractical for maintaining any coherent civilization across it. The round-trip trap makes most interstellar destinations effectively one way for any purpose of returning useful knowledge to the civilization that sought it. But even setting all of that aside, even accepting all of those constraints as costs that some sufficiently determined and long-lived civilization might absorb, there is a physical feature of the universe that imposes an absolute limit on what is reachable at any speed. Up to and including light speed, the universe is expanding. This is not a metaphor or a theoretical prediction still awaiting confirmation. It is the most thoroughly observed and measured fact in cosmology. The galaxies and galaxy clusters beyond our local gravitational neighborhood are receding from us. The farther away they are, the faster they are receding. This recession is not because those galaxies are moving through space toward us. It is because space itself is expanding. New space is being created between all the gravitationally unbound structures in the universe, carrying them apart from each other, the way raisins in a rising loaf of bread move apart from each other, not because the raisins are moving, but because the bread between them is growing. This expansion was first observed by Edwin Hubble in 1929, when he noticed that the spectral lines of light from distant galaxies were shifted toward the red end of the spectrum, indicating that those galaxies were moving away from us. The greater the distance, the greater the redshift, the faster the recession. This is now called Hubble's law, and its observational confirmation is so robust that it forms the foundation of modern cosmology. In 1998, two independent teams of astronomers studying distant supernova explosions made a discovery that won the Nobel Prize in Physics in 2011. The expansion of the universe is not merely continuing at a constant rate, it is accelerating. The recession velocity of distant galaxy groups is increasing over time. Something which physicists call dark energy, a property of empty space itself whose ultimate nature remains unknown, is causing the expansion to speed up. The universe is not just expanding, it is expanding faster and faster. This acceleration has a consequence that is often overlooked in discussions of faster-than-light travel. It creates a cosmic event horizon, a boundary in space beyond which, even travelling at the speed of light, you can never reach a galaxy that currently sits on the other side. Here is why. At a certain distance from Earth, the recession velocity of space equals the speed of light. That distance is roughly 14 billion light-years. A galaxy currently sitting 14 billion light-years away from us is receding at exactly the speed of light. If you launched a light-speed ship toward that galaxy today, the ship would be chasing a galaxy that is moving away from it at exactly the same speed it is approaching. The ship would never gain on the galaxy. The distance between them would remain constant, or worse, grow, as the acceleration of the expansion slowly pushes the recession velocity above light speed. Galaxies beyond that 14 billion light-year boundary are receding faster than light. A ship launched at light speed towards such a galaxy would fall farther and farther behind. The galaxy is moving away from the ship faster than the ship can approach. No matter how long the ship travels at light speed, the galaxy moves farther away. The ship can never reach it. This creates the cosmic event horizon, a surface in space that divides the universe into two regions. The region that is, in principle, reachable at light speed given enough time, and the region that is not reachable at any speed up to and including light speed, because the expansion is carrying it away too fast. Currently, only galaxies within roughly 16 billion light-years of us are on the reachable side of the cosmic event horizon. Galaxies beyond that distance are permanently and irreversibly beyond reach, not just practically but in a fundamental physical sense. No amount of time, no amount of determination, no amount of additional speed up to and including exactly light speed will ever allow you to reach them. They are gone, physically and finally, from any possible future interaction with anything in our observable universe. And because the expansion is accelerating, the cosmic event horizon is not fixed, it is shrinking. Galaxies that currently sit just inside the horizon will, as the years pass and the expansion continues to accelerate, eventually cross to the other side and become permanently unreachable. The territory accessible at light speed is contracting, slowly and continuously, as more and more of the universe disappears beyond the receding horizon. In roughly 150 billion years, all of the galaxies currently visible to us except for the Milky Way and the small local group of roughly 50 gravitationally bound galaxies around it will have receded beyond the cosmic event horizon. The night sky, for any civilization still existing at that time, will be essentially dark. The universe that was once filled with 2 trillion galaxies will appear, from our gravitational neighbourhood, to contain only the few dozen galaxies held together by our local gravity. Everything else will be gone, irreversibly, permanently, beyond any possible physical reach. We are right now living through the era of the universe with the greatest visibility and the greatest theoretically accessible territory. In the deep future, after the acceleration of expansion has had more time to act, the universe will be darker and more isolated than it is today. We are, in a real sense, missing windows of opportunity with every passing year. This does not mean anything urgent for any human timescale. The contraction of the accessible universe is slow in human terms, though fast in cosmological terms. But it underscores something important about the light speed limit. It is not just a speed limit on motion through space. It is, in the context of an expanding and accelerating universe, a limit that will become more and more restrictive over time. The universe is not a fixed territory waiting to be explored at light speed. It is a shrinking territory, and light speed is not fast enough to keep up with the shrinkage. And there is one more consequence of the expansion that deserves attention, because it affects not the far future, but the present. The galaxies we observe when we look at the night sky are not where they appear to be. The light reaching our eyes and our telescopes left those galaxies millions or billions of years ago, when they were much closer to us. In the time that light has been travelling, those galaxies have continued to recede. They are now much farther away than the light travel distance suggests. A galaxy whose light took 10 billion years to reach us, and which therefore appears to be 10 billion light years away, is actually, right now, roughly 28 billion light years away, because it has been moving away from us for the 10 billion years that its light was in transit, and space has been expanding throughout that time. The observable universe has a light travel radius of about 46 billion light years, but its actual current radius, accounting for the expansion during the travel time of the light we observe, is about 46 billion light years. And its co-moving radius, the distance accounting for all the expansion, is larger still. What this means is that the observable universe, which looks like a sphere 92 billion light years across in terms of current distances, already extends well beyond what a light-speed ship launched today could ever reach. Even the most distant galaxies we can currently see are receding from us faster than light. Their light reached us because they were close enough when that light was emitted, but the galaxies themselves are now beyond the cosmic event horizon. We can see farther than we can ever go. The universe is already, right now, showing us things it will never allow us to reach. The visible universe and the reachable universe are not the same thing, and the reachable universe, even at light speed, is a much smaller and much simpler place than the universe we can observe. The cosmic event horizon is not a static boundary, it is a dynamic one, and its dynamics reveal something important about the long-term trajectory of the universe. Right now, in this epoch of cosmic history, the horizon sits at roughly 16 billion light-years from Earth. But the universe is expanding, and the expansion is accelerating. The boundary is not fixed at 16 billion light-years, it is slowly retreating. Galaxies that are currently just inside the reachable zone are gradually being pushed toward the horizon and eventually across it. The territory accessible at light speed is contracting. This is already happening. Astronomers have identified galaxy groups that are currently borderline in terms of their accessibility at light speed, close enough to be reachable in principle, but receding fast enough that a light-speed ship launched today might only barely catch them, or might fail to catch them depending on the precise current recession velocity. These are the first galaxies to be definitively lost to us, in the sense of crossing the horizon before any civilization could realistically mount a light-speed mission to reach them, and the rate of loss will accelerate. As the universe expands and the expansion speeds up, more and more galaxies will cross the horizon per unit of time. The rate at which territory is lost to us is increasing. We're in the epoch of greatest galactic visibility, the epoch where we can see the most galaxies and, in principle, reach the most of them. That epoch has already passed its peak. It is declining slowly but inexorably. In roughly 100 billion years, the Milky Way and its local group companions will be the only structures remaining within our cosmic event horizon. All other galaxy groups and clusters will have receded beyond reach. The night sky will be dark. The universe that once appeared as a dense field of galaxies in every direction will appear, from our gravitational neighbourhood, to contain only a handful of nearby galaxies bound to us by gravity. Everything else will be gone. From the perspective of any civilization that exists at that time, the universe will appear much smaller and much simpler than it appears to us now. They will see a local group of galaxies surrounded by apparent emptiness. They will not know, unless they have the historical records to tell them, that the emptiness was not always empty, that once there were 2 trillion galaxies scattered across the sky, all now beyond reach and beyond sight. We know this now. We can see those galaxies. We can measure the expansion. We can calculate when each galaxy group will cross the horizon. We are, in a real sense, the privileged generation, living in the epoch of maximum cosmic visibility and maximum theoretical accessibility. And one of the things our privileged vantage point allows us to see is that light speed is not fast enough to preserve that visibility. Light speed cannot chase the horizon. Light speed loses the race. This adds a dimension of genuine urgency to the faster-than-light problem that is rarely acknowledged. The problem is not merely that we want to reach other stars for the reasons that have always motivated exploration. Curiosity, the desire for knowledge, the desire for connection, the desire to understand where we live and whether we're alone. The problem is also that the window for accessing the broader universe is closing, slowly, imperceptibly on any human timescale, but closing. If there are civilizations to be found and contacted in the broader universe beyond the local group, the window for contact is finite. Eventually those civilizations will be beyond any possible reach, not because they cease to exist, but because the space between us and them has grown beyond what any signal or ship moving at or below light speed can cross. The conversation that might happen, the exchange of knowledge and perspective between civilizations that arose in different corners of the universe, has a deadline, and light speed cannot meet that deadline. Only something faster than light could keep pace with the expanding universe, and the question of how much faster depends on how long the window actually remains open, which depends on the acceleration of the expansion, which depends on the nature of dark energy, which is currently not understood. We are facing the possibility that the universe is structured, not through any malice, but through the pure mechanics of its own physics, to separate its own contents from each other over time. To produce a universe that is increasingly fragmented, increasingly isolated, increasingly composed of local groups marooned from each other by an ever faster expansion of the void between them, and to ensure that any technology developed across that void must operate faster than the speed of light just to keep pace with the recession, let alone make meaningful contact on timescales relevant to any civilization. The universe appears to be optimized for isolation, and light speed participates in that isolation rather than resolving it. And now we come to the physical dimension of the problem, the one that applies not to civilizations but to ships, not to communication delays but to survival in the environment of interstellar space at extreme velocities. Because the universe does not merely present a practical problem for light-speed civilizations through the mechanisms of distance and time dilation and communication delay. It also presents a physical problem. The environment of interstellar space becomes increasingly hostile as you approach the speed of light, in ways that compound each other and that converge, at truly extreme velocities, on conditions that no physical structure made of matter could survive. We discussed earlier how the cosmic microwave background radiation, the faint thermal afterglow of the Big Bang that fills the entire universe uniformly, becomes progressively more energetic from the perspective of a fast-moving ship. At low speeds, the CMB is cold and harmless, microwave photons too weak to affect anything. At high fractions of light speed, those same photons are blue-shifted. Their frequency rises, their energy rises. By 90% of light speed, the CMB photons arriving from ahead of the ship appear as X-rays. By higher fractions, they appear as hard gamma radiation. Hard gamma radiation is the most penetrating form of electromagnetic radiation. It passes through most materials with little absorption. The thicker you make the shielding, the more you reduce the dose, but the mass penalty for meaningful gamma radiation shielding is severe. And at truly extreme fractions of light speed, the CMB photons are not just mildly gamma, they're extremely energetic gamma radiation, far beyond the softer end of the gamma spectrum where shielding strategies might be marginally effective. At exactly the speed of light, the Lorentz factor is infinite. The blue shift of the CMB photons from ahead would be infinite. Each photon arriving from ahead would have infinite energy. This is not a physical state. No material structure can interact with infinitely energetic photons and remain intact. The concept of a physical ship made of matter travelling at exactly light speed is not merely energetically impossible. It is thermodynamically incoherent. The environment at light speed would not just kill the crew. It would disaggregate every atom in the ship in an instant. This is why the idealized scenario, imagine we could travel at the speed of light, is not quite physically meaningful for any object made of matter. Light travels at light speed because it has no mass. Mass cannot reach light speed. The energy required diverges to infinity as the velocity approaches the limit. And even if the energy were somehow available, the physical environment at or near light speed would destroy any structure made of matter long before the speed was reached. The practical ceiling for any ship made of matter is some velocity below light speed. And because the physical hostility of the environment increases steeply as you approach the limit, the practical ceiling may be significantly below light speed, when the radiation environment is balanced against any shielding mass that a rocket equation-constrained ship can carry. The same time dilation that makes extremely high fractions of light speed attractive, the time dilation that compresses the crew's subjective journey time towards zero, is achievable only at the velocities where the CMB radiation environment becomes most severe. The physics that would give you the subjective experience of instantaneous crossing also places you in an environment that no known material can withstand. The two effects are inseparable. They come from the same relativistic mathematics. You cannot have the extreme time dilation without the extreme CMB blue shift. This means that the true practical limit for crewed travel is likely somewhere between 50 and 90% of light speed, depending on what shielding strategy is available, what radiation dose is acceptable, and what mission duration is required. Probably closer to the lower end of that range when all the constraints are applied simultaneously. And at those velocities, the time dilation is significant but not extreme. A journey to Proxima Centauri at 50% of light speed takes about 4.9 years from Earth's perspective and about 4.3 years from the crew's perspective. A journey to a star 100 light-years away takes about 200 years from Earth's perspective and about 175 years from the crew's perspective. These are not light-speed journeys, they are sublight journeys, and they face all the problems of sublight journeys: the rocket equation, the multi-generational crew, the institutional patience required, the radiation environment, all of which we explored in detail earlier in this conversation. The speed of light is not a destination that matter can reach. It is a mathematical horizon that matter can approach asymptotically but never touch. And in approaching it, matter enters an increasingly hostile physical environment that pushes back harder and harder against every increment of additional velocity. So the light speed problem is, at its core, not actually about light speed. It is about the gap between what light speed represents and what it would actually deliver. Light speed, even if achieved, does not solve the human problems of interstellar civilization. It solves the travel time problem for the traveller while creating the time dilation problem for the civilization. It solves the problem of getting there while creating the problem of the civilization having moved on before you can return. It solves the problem of the journey duration while creating the problem of arriving in a future you did not participate in building. And it does not even solve the travel time problem at galactic scales. Even at exactly light speed, even with the full benefit of infinite time dilation that compresses every journey to a single subjective instant, you're still subject to the full light travel time as experienced by everything you left behind. The galactic center is still 26,000 years away for Earth. Andromeda is still 2.537 million years away. The cosmic event horizon is still where it is. Lightspeed gives the crew a ticket to destinations their civilization will never recognize. At times, their civilization will never see. There is a thought experiment that makes the physical impossibility of matter at light speed vivid. Consider what it would mean to accelerate a single proton, the nucleus of a hydrogen atom, to the speed of light. The proton has a rest mass of about 1.67 times 10 to the minus 27 kilograms. At rest, its mass energy, expressed through Einstein's famous equivalence, is about 938 million electron volts. As the proton accelerates, its relativistic mass increases according to the Lorentz factor. At 90% of light speed, its effective mass is about 2.3 times its rest mass. At 99%, about 7 times. At 99.9%, about 22 times. To accelerate the proton to light speed, the Lorentz factor would need to become infinite. The proton's effective mass would need to become infinite. To accelerate an infinite mass requires infinite force applied over infinite distance, or infinite energy applied over infinite time. Neither of these is physically achievable. The proton cannot reach light speed, not with any finite amount of energy, not with any finite duration of acceleration. The wall is not steep, it is infinite. Now consider that a ship contains not one proton, but approximately 10 to the 28th power of them, plus a comparable number of neutrons and electrons. Each one faces the same infinite energy requirement to reach light speed. The ship as a whole cannot reach light speed. The prohibition is absolute, arising from the basic structure of the mass-energy relationship in special relativity. What this means is that when we discuss travelling at the speed of light, we are always discussing an idealization. A limit case, a thought experiment, not a physical possibility for any ship made of matter. The speed that would actually be achievable with unlimited energy would approach light speed asymptotically. You could get arbitrarily close. You could get to 99.9999999%, spending ever-increasing amounts of energy on each additional 9, but you could never arrive at the number itself, and at the velocities where the time dilation becomes extreme enough to compress the crew's subjective journey, time to something approaching zero. The physical environment is also extreme. The CMB radiation, the interstellar dust, the galactic magnetic field, the quantum vacuum interactions, all of these become progressively more hostile as velocity approaches light speed. The regime of maximum time dilation is also the regime of maximum physical hostility. The physics that would give you the zero subjective second journey also places you in an environment that destroys any known material structure. The asymptote is not just energetically inaccessible, it is physically lethal at every practical approach to it. The environment defeats you before the energy requirement does. And so the relevant question for any actual mission is not what happens at light speed, but what happens at the maximum practically achievable velocity. The velocity below light speed at which the combination of shielding mass, radiation environment, energy source, and structural integrity allows a mission to function and survive. That velocity is substantially below light speed, certainly below 90%, probably below 80% for any crewed mission with a realistic shielding budget, possibly considerably lower than that. At those velocities, the time dilation is significant but not extreme. The crew subjectively experiences most of the journey time. A crossing to Proxima Centauri takes several years. A crossing to a star 100 light-years away takes well over a century. The benefits of time dilation are real, but do not compress the journey to anything like zero. And all the challenges of sublight travel, the rocket equation, the institutional patience, the multi-generational crew, the communication delays, remain fully in force. The practical limit for matter is not light speed. It is somewhere in the range of 50 to 80% of light speed, depending on engineering constraints and acceptable mission risk. And at that range, the problems are not solved. They are merely somewhat reduced compared to the speeds currently achieved, while being enormously harder to achieve than current speeds. Light speed in this context is not a goal. It is a mathematical limit in the equations, the asymptote toward which you might push but that you can never reach, in an environment that becomes progressively more hostile as you approach it. The dream of travelling at the speed of light is, for matter, literally a dream. An asymptotic fantasy that the physics systematically prevents from being realised. The aspiration should not be to reach light speed. The aspiration should be to achieve the speeds that would actually solve the problems of interstellar civilization, which are substantially greater than light speed, achieved by some mechanism other than conventional propulsion pushing matter through space. And that aspiration requires not just better engineering of conventional propulsion, but a fundamentally different approach to the problem of crossing interstellar distances. So what would fast enough actually look like? If light speed is insufficient, if it fails not at the physics level but at the human level, at the civilizational level, at the level of what exploration and connection and return actually require, then what speed would be sufficient? What would the target actually be, if not the speed of light? The answer requires specifying what we mean by sufficient, what the mission of a successful interstellar civilization would actually look like. What success means in this context. Let us define it concretely. A successful interstellar civilization is one in which a ship can depart from a homeworld, reach an interesting destination, conduct meaningful observations or interactions, and return with its findings to a civilization that still has the institutional memory and cultural continuity to receive and act on what was learned. A civilization where the knowledge generated by a mission flows back into the living body of the civilization that sought it. Where the explorers come home, and home is still home. For this to work, the round-trip travel time as experienced on Earth must fall within the span of institutional and cultural continuity. For a large, stable, long-lived civilization, this might be a few hundred years. For a civilization explicitly organized around multi-generational commitments, perhaps 1,000 years at the most optimistic estimate. Let us use 1,000 years as a generous upper bound. At the speed of light, 1,000 Earth years of round-trip time allows you to travel 500 light-years out and 500 light-years back. That covers a sphere roughly 1,000 light-years in diameter around your home world. The Milky Way is 100,000 light-years across. A 1,000 light-year sphere contains roughly 0.000001% of the galaxy's volume. It is not a civilization, it is a neighborhood. But the calculation uses light speed, which gives the traveler zero subjective journey time. If we allow the crew to experience some journey time, using a speed slightly below light speed, the situation is even more constrained. At 99% of light speed, the crew experiences about 14% of the Earth time for each leg. A 500 light-year journey takes about 500 years on Earth and about 70 years for the crew. That is still a long mission, requiring multi-generational organization even from the crew's perspective, and 500 light-years is still a tiny fraction of the galaxy. To reach the galactic center, 26,000 light-years from Earth, and return within 1,000 Earth years, you need a ship that completes the round trip of 52,000 light-years in 1,000 Earth years. That requires traveling at 52 times the speed of light, not 52% of light speed, 52 times light speed, substantially faster than light. To reach Andromeda, 2.537 million light-years away, and return within 1,000 Earth years, you need a ship traveling at roughly 5,000 times the speed of light. To reach the Virgo cluster, 53 million light-years away, within 1,000 Earth years, you need a ship traveling at roughly 106,000 times the speed of light. These are not marginal improvements over the speed of light. They are not the difference between light speed and slightly faster than light speed, the difference between a grade of fail and a grade of barely pass. They are orders of magnitude beyond the speed of light. They represent a physical regime so far beyond current theoretical understanding that we cannot even confidently say whether the equations permit them, let alone how such speeds might be achieved. But the requirement is clear, and requirements have a way of forcing clarity. The speed of light is not the goal. It is the first marker on the road, the marker that says you have crossed the threshold of conventional physics into the regime where the fundamental rules change. But crossing that threshold at one time's light speed does not put you in a useful place. It puts you in a place where the problems of interstellar civilization are ameliorated for the traveler and catastrophically worsened for the civilization. You need to go much, much faster than light to be in a place where the problems are actually solved. And here is the strange implication of all this analysis for the question of the Fermi paradox, the question that has been woven through this entire conversation. The Fermi paradox asks why we see no evidence of extraterrestrial civilizations, given how many stars and planets there are, and how long the universe has existed. The most common technological framing of the paradox focuses on the difficulty of reaching or even achieving light speed. But we have just shown that light speed is not the relevant threshold. Light speed is insufficient for galactic civilization. The relevant threshold is the speed at which the round-trip time to interesting destinations falls within the span of civilizational continuity. That threshold, at a minimum, requires tens of times the speed of light for galactic-scale exploration. It requires thousands of times light speed for intergalactic ambitions. If that threshold has never been crossed by any civilization in the history of the galaxy, then the Fermi paradox has a clear answer. The universe is not silent because there is no one out there. It is silent because no one has achieved the speeds that would allow the kind of expansion and contact and broadcasting that would make a civilization detectable across interstellar distances on any practical timescale, not just light speed, the speeds that matter, the speeds that would allow exploration to be exploration, that would allow missions to return meaningful knowledge, that would allow civilizations to span the galaxy and remain coherent enough to be recognizable as civilizations. The silence of the sky may not be the silence of an empty universe. It may be the silence of a universe full of civilizations that found the wall, understood that light speed was merely the wall's first face and not its final depth, and are still looking for the door, still calculating, still searching the equations, still wondering whether the mathematics that permits so much strange and beautiful geometry might somewhere, in some regime not yet explored, permit the speeds that would make the cosmos actually navigable. There is one more calculation worth making explicit, because it reframes the entire conversation in a way that is rarely done. We have established that meaningful interstellar civilization, defined as civilization that can explore and return and communicate and remain coherent, requires round-trip times on the order of centuries to perhaps a millennium as experienced on Earth. And we have established that achieving those round-trip times for destinations beyond a few hundred light-years requires travelling at speeds substantially greater than light speed. But let us ask a different version of the question. What if we relaxed the coherence requirement? What if we accepted that a light-speed civilization would not be a single civilization, but a branching tree of related but increasingly divergent civilizations? What would that actually look like over cosmological time? Imagine that humanity achieves light-speed travel and begins settling nearby star systems. The first wave of colonists travels to stars within a few dozen light years. Each colony, from the moment it is established, begins to diverge culturally and genetically from Earth. The divergence is slow at first, because the colonies maintain communication with Earth and with each other, even at light-speed communication delays of years and decades. But over centuries the divergence accelerates as local conditions shape local cultures, as local scientific communities develop their own frameworks, as local political and religious and social institutions evolve in their own directions. After 1,000 years, the light-speed civilization contains dozens of worlds, each distinct from the others, each communicating with the others at delays ranging from years to decades. The communication still flows, knowledge still crosses the distances. But the knowledge is already becoming increasingly specific to local contexts, increasingly difficult to translate across the growing cultural divides. After 10,000 years, the civilization contains hundreds of worlds spread across a volume thousands of light years across. Communication delays range from decades to millennia. The worlds near the periphery of the expansion receive transmissions from Earth that describe events thousands of years ago. The events are historical artifacts by the time they arrive, context for understanding the distant past, not guidance for navigating the present. After 100,000 years, the civilization has reached the galactic scale. It covers a volume perhaps 50,000 light-years across. The oldest worlds have had 100,000 years to evolve independently. Their relationships with Earth are purely historical. The languages spoken on the oldest colony worlds share no more than a few root words with any language spoken on Earth, if that. The religions have transformed beyond recognition. The scientific frameworks have diverged so completely that the same physical phenomenon is described using incompatible conceptual structures on different worlds. Is this a civilization? In what sense? It shares a common origin. It shares a genetic heritage, though that too has diverged under the pressures of different planetary environments. It shares, perhaps, a founding mythology. A story about leaving a small blue planet and spreading through the galaxy. But it does not share governance. It does not share culture. It does not share language. It does not share a scientific community. It does not share anything that would allow one part of it to coordinate meaningfully with another part, or to recognize the other part as itself. It is not a galactic civilization. It is a galaxy full of civilizations that share an ancestry. The same way that all of humanity, which spread out of Africa beginning roughly 70,000 years ago, shares an ancestry, but has not been a single coherent civilization for most of that time. Lightspeed produces, at galactic scales, not a civilization but a diaspora, a spreading of related but distinct populations, each evolving independently, each developing its own identity, each progressively less connected to the common origin and to each other. The galactic diaspora would be richer in terms of the total knowledge and experience generated than any single civilization. But it would not be a single civilization. It would be thousands or millions of civilizations, related but distinct, communicating across distances too large for any meaningful shared purpose to be maintained. And this is worth naming as a possible future, neither utopian nor dystopian, neither a triumph nor a failure, just a consequence. If light speed is the best that physics permits, then the galactic diaspora is probably the best that civilization can achieve. Not coherent galactic civilization. An immense branching family of related but distinct civilizations, each living in its own local cosmos, each occasionally receiving echoes from its distant relatives, each contributing its own unique experience to the total record of intelligence in the universe. There are worse outcomes. A universe in which intelligence does not spread at all, in which each civilization lives and dies on its home planet without leaving any trace beyond its immediate stellar neighborhood, is a lonelier and a smaller thing. The galactic diaspora, if that is what lightspeed produces, would at least be present, at least be active, at least be generating experience and knowledge and art and mathematics and all the other things that intelligent beings generate when they have time and freedom. But it is not the connected, communicating, coherent galactic civilization that the imagination reaches for when it thinks about humanity becoming a spacefaring species. That civilization requires something that light speed cannot provide, something faster, something that keeps the round-trip time short enough for institutional and cultural continuity, something that allows news to flow and missions to return and knowledge to circulate and relationships to be maintained across the distances between worlds. The name for what is needed is faster than light, but the precise requirement is specific, not barely faster than light, not 1.001 times the speed of light, substantially faster, fast enough to compress the galaxy to navigable proportions, fast enough to allow a ship to go somewhere interesting and come back within the span of living memory, fast enough to make the stars feel not close, but reachable in a way that makes sense within the timescale of human life and human purpose. We do not know if the physics allows this. We are still finding out. And so we come to the close of this mission briefing, and to the question that the mathematics has been building toward throughout. The speed of light is not the answer to the problem of reaching the stars. It is the problem more precisely stated. It is the speed at which the universe's own maximum limit still leaves the cosmos impossibly large, still leaves civilizations impossibly isolated, still leaves explorers unable to return to the world they left without finding it transformed beyond recognition. The universe has not been unkind in giving us this limit. It has not been cruel or arbitrary. The speed of light is what it is because of the deep structure of space-time, the precise way that space and time are woven together into the fabric that everything inhabits. It is a consequence of the geometry, not an imposition on top of it. It is what physics looks like at its most fundamental level, and at that level it is beautiful. The elegance of the equations, the way time and space trade off against each other at precisely this constant, is one of the most remarkable features of the universe we live in. But beauty does not make the distances shorter, and elegance does not make the round trips faster. What this analysis reveals, when followed to its conclusion, is that the aspiration toward interstellar civilization is not an aspiration toward light speed. It is an aspiration toward speeds we do not yet know how to achieve, in a physical regime we do not yet fully understand, using mechanisms we have not yet confirmed are permitted by the laws of nature as we currently understand them. That is honest. It is also not a reason to stop. The history of physics is the history of finding that previous frameworks were incomplete at certain scales or velocities or energies. Newtonian mechanics was sufficient for all practical purposes until the 19th century began producing phenomena it could not explain. Then Maxwell's electromagnetism changed the picture. Then Einstein's special relativity changed it further. Then general relativity deepened it. Then quantum mechanics rewrote everything at the small scale. At each transition, the new framework revealed a physical reality more strange, more rich, and more permissive in unexpected ways than the previous framework had suggested. We are almost certainly still inside a framework that will prove incomplete in some regime. The reconciliation of general relativity and quantum mechanics, which remain fundamentally inconsistent with each other at the mathematical level despite each working beautifully in its own domain, is the most obvious open wound in fundamental physics. Quantum gravity, whatever it turns out to look like, will be a new framework. And new frameworks have a way of permitting things the previous framework could not accommodate and prohibiting things the previous framework seemed to allow. The specific regime of extreme superluminal motion, speeds many times greater than light speed, may be exactly the kind of regime where the current framework is incomplete and where the new framework changes what is possible. We cannot know this from inside the current framework. We can only note that the current framework already allows, in its exotic solutions, things that seem on the surface to be as strange as faster-than-light travel. Black holes, wormholes, the expansion of space beyond light speed, quantum entanglement, which produces correlations that seem to ignore the light speed constraint, even though they cannot be used to transmit information faster than light. The strangeness is already present. The edge of the current framework is already visible. Whether what lies beyond that edge contains the speeds that would make galactic civilization possible, we cannot yet say. What we can say is what success looks like. We can specify the target. We know that light speed is not enough. We know that the threshold for meaningful interstellar civilization, defined as a civilization that can explore and return and communicate and remain coherent, requires speeds substantially greater than light speed. We know the minimum multiple of light speed required to make each destination of interest accessible within a civilizationally meaningful round-trip time. We know the requirement, even if we do not know the path. And knowing the requirement is the beginning of engineering. Requirements do not solve themselves, but they focus the inquiry. They tell you what to look for. They rule out the partial solutions that seem promising, but fall short of what the problem actually demands. They prevent the mistake of celebrating a capability, like light speed, that is genuinely remarkable without being sufficient. They keep the goal clearly in view, even when the path to it is invisible. The goal is not light speed. The goal is civilizational coherence across cosmic distances. The goal is exploration that returns, knowledge that circulates, missions that mean something to the people who launch them. The goal is a universe that feels, not small. The universe will never feel small but navigable. A universe where the gap between stars is a journey and not a permanent exile. Where the crew that goes out comes back to something it recognizes as home. We do not know if the physics allows this. We know that the physics as currently understood does not obviously permit it and might prohibit it at the speeds required. We know that every exotic solution to the current equations, every wormhole and warp bubble and accelerating spacetime, brings with it new problems in exchange for every problem it solves. We know that the universe has a way of being more restrictive than we hope and more permissive than we fear, and that the final answer about what is possible is still being written. We know that we are early, a species 300 years into technological civilization, a few decades into spaceflight, a few years into the systematic study of whether the equations permit any form of faster-than-light geometry. We have barely begun mapping the territory. The speed of light is not the finish line. It is the starting point for the questions that actually matter. And those questions are wide open, so we keep measuring, we keep calculating. We keep following the equations wherever they lead, even into territory that's uncomfortable, even into conclusions that say the problem is harder than we hoped, even into the recognition that what we really need is not what we thought we were aiming for. Because that recognition is not failure, it is precision. And precision is always the first step. There is something worth saying about the experience of confronting this problem at this particular moment in history. We live in the first generation that knows, with real precision, how large the universe actually is. For most of human history, the stars were points of light at unknown distances. The idea that they might be suns like our own was speculation. The distances between them were not measured until the 19th century. The full scale of the galaxy was not established until the early 20th century. The existence of other galaxies beyond the Milky Way was not confirmed until 1923, when Edwin Hubble resolved individual stars in the Andromeda Nebula and demonstrated it was a separate galaxy entirely. The age of the universe was not measured with real precision until the 1990s. We are extraordinarily recent inheritors of knowledge that our species did not possess even within the memory of people still alive. And that knowledge, taken seriously, reveals a universe so vast that even the fastest possible speed still leaves it, for all practical civilizational purposes, almost entirely unreachable. This is not comfortable. It sits uneasily alongside the ambitions that the same knowledge produces. Knowing that other stars exist, knowing that some have planets in their habitable zones, knowing those planets might harbour life, naturally produces the desire to reach them. And knowing that reaching them at any speed currently imaginable would take thousands or millions of years produces a specific kind of frustration. The frustration of seeing something clearly and being unable to touch it. But the gap has a shape. It is not formless. It is defined by specific physical laws with specific numerical implications for what speeds are required to close it. And a gap with a precise shape is a gap that can, at least in principle, be addressed. The problem of reaching the stars does not dissolve because we have mapped the reasons for the difficulty. But mapping the reasons is the necessary first step toward anything that comes after. We know what is out there, we cannot reach it. The gap between what we know and what we can do is large, and the gap between what we can do and what would actually be sufficient, the gap between our fastest conceivable propulsion and the speeds needed for meaningful galactic civilization, is even larger. The speed of light is not the goal. It is one data point in a much larger calculation. The people who first measured the distance to Proxima Centauri in 1917 did not imagine that their great-grandchildren would be designing probes capable of reaching it within a human generation. They measured a distance that had no conceivable engineering solution attached to it. And yet the engineering conversation about actually visiting Proxima Centauri's planetary system, while still aspirational, is real. The distance did not shrink. The ambition grew to meet it. The timescale for the faster-than-light problem is longer. The physics is more fundamental. The obstacles are more deeply embedded in the structure of space-time itself. But the direction of travel in our understanding is the same. The problem is being mapped. The requirements are being calculated with precision. The edges of current understanding are being probed by experiments and by mathematics that previous generations could not have imagined. What this generation owes to the ones that come after is not a solution. We almost certainly cannot provide that. What we owe them is the precise specification of the problem, the clear identification of what is required, what the physics suggests is permitted where the map of current understanding ends, and what the most promising directions for extending that map might be. That cartographic work is being done now, and doing it carefully and precisely is the contribution this moment in history can make to whatever comes next. The speed of light is not enough. That is now known with precision. Substantially faster than light is required, by specific amounts that can be calculated from specific assumptions about what civilization actually needs. The mechanisms that might achieve it are speculative but not obviously prohibited by any proven theorem. The experiments to test whether relevant geometries correspond to physical reality are being designed and in some cases conducted. This is progress. Not the kind that changes travel time to any star within any human lifetime. The kind that matters over the longer arc of inquiry. The kind that eventually, through generations of work and unexpected discoveries, might produce something that changes everything about the problem. The universe is large. It is indifferent to our timelines. It has structured itself through its own physics in ways that resist exactly what intelligence most desires from it. And still we keep looking, we keep calculating. We keep mapping the walls. That is what it means to be at this moment. Consider what it would mean for this to be true. For the silence to be evidence not of absence, but of a shared constraint. Every civilization in the galaxy, every intelligence that has ever arisen on a rocky world around a stable star, facing the same mathematics, the same 299,792 kilometers per second, the same impossibly large distances, the same exponential energy costs, the same time dilation that disconnects travelers from their home civilization, the same recognition that even if you reached the speed of light, even if you solved every engineering problem and overcame every known obstacle, the universe would still be too large and too fast and too indifferent to your timelines for any coherent civilization to span it. Every civilization running the same calculation, every civilization arriving at the same conclusion. Light speed is not enough. Something faster is required, and something faster, as far as any of them has been able to determine, is not available. The Fermi paradox in this reading is not a paradox at all. It is the universe demonstrating through the very silence that puzzles us that the speed of light is a wall not just for us but for everyone, that the threshold required for galactic civilization has not been crossed, that the door in the wall, if it exists, has not been found by any civilization in the 13 billion years the galaxy has been old enough to host them. This does not mean the door does not exist. Absence of evidence is not evidence of absence, and the silence of the radio telescopes is consistent with many different explanations, including the explanation that no civilization has yet found the key. It means we have no positive evidence that the door exists. We have only the fact that we are looking for it, and that looking is itself evidence that we believe, or at least hope, that it might be there. And hope, in the context of physics, is a form of prior probability, a sense that the universe, which has been so permissive in so many unexpected ways, so full of strange and beautiful geometries and phenomena that no previous framework predicted, might yet contain one more surprise, one more region of the map that the current framework underestimates. The warp drive exists in the equations, the geometry is mathematically valid, the obstacles are real but not proven insurmountable. The experiments to test whether microscale warp effects are physically realizable are being designed. The gap between what the mathematics permits and what engineering can achieve is large. but gaps between mathematical permission and engineering achievement have been closed before in directions that seemed unpromising until they suddenly were not. We are, in the grandest sense, still at the beginning, barely emerged from our home planet, barely arrived at a mature understanding of the scale of what we inhabit, barely begun the systematic investigation of whether the rules permit the speeds that would make the cosmos navigable. A species at the very earliest stage of what might, if the physics allows it, become a much longer story. The speed of light is the beginning of that story's central question, not the answer, the question. What comes after light speed? What does the universe permit beyond it? Is there a regime of physics yet undiscovered that contains the mechanisms needed for the speeds that would actually matter? These are the questions that define this moment in human history. And this moment, for all its frustrations and limitations, is a remarkable one to inhabit, because for the first time the questions are being asked with precision, with mathematics, with experimental programs, with the tools that have historically produced answers. The universe is still mostly unknown, the map is still mostly blank, and blank maps have always been the most interesting ones. One more thing deserves to be named before this mission briefing ends. Something that is easy to lose sight of when the focus is on distances and timescales and speeds that dwarf human experience. The reason we care about all of this is not abstract. It is not an exercise in cosmological bookkeeping. It is not a detached catalogue of obstacles for some future generation to solve while we watch from a comfortable distance. We care because we are curious. We care because somewhere in the structure of human consciousness, in the part of us that learned to look at the night sky and feel something other than indifference, is a genuine hunger to know what is out there. Not a metaphorical hunger, a real one. The same one that drove every explorer who has ever lived to face the unknown rather than retreat from it. The same one that built the telescopes and the particle accelerators and the space telescopes. The same one that keeps theoretical physicists working late into the night on equations that might never produce a practical result within their lifetime. That hunger is not going anywhere. It is one of the most consistent things about our species, and the fact that the universe has built walls around the territory the hunger reaches for does not extinguish the hunger. If anything, it sharpens it. A wall with a known location is more interesting than an unknown obstacle. A problem with precisely stated dimensions is more tractable than a vague impossibility. The fact that we can now calculate with real precision how much faster than light we would need to travel to make galactic civilization coherent, to make exploration genuinely meaningful rather than merely physically possible, is a kind of progress. It transforms the aspiration from a dream into an engineering requirement. And engineering requirements, unlike dreams, can in principle be met. The requirement is enormous. The path to meeting it is unclear. The physics may ultimately prohibit it, but the requirement is stated, and that is more than any previous generation had. The universe did not give us the stars close enough to touch. It gave us eyes good enough to see them, minds curious enough to wonder about them, and mathematics precise enough to calculate exactly how far they are and exactly how fast we would need to travel to reach them meaningfully. That combination, sight and wonder and calculation, is perhaps the universe's way of being generous within the constraints of its own laws. It shows us what is there. It does not yet tell us how to reach it, but showing is the first step, and we are looking. We began this mission briefing with a thought experiment. Imagine you solved the hardest problem in physics. Imagine light speed was achieved. The thought experiment was designed to reveal something that is easy to miss when the conversation is focused on the difficulties of reaching light speed. The focus is usually on the energy requirements, the engineering challenges, the exotic matter, the causality paradoxes. All of those things are real, but they are obstacles on the path to light speed. What we have explored tonight is what lies past those obstacles. What is on the other side of the wall? Whether crossing the wall, if crossing it were possible, would deliver what we hope it delivers. And the answer is, not quite. Not at galactic scales. Not for any civilization hoping to remain coherent across the distances involved. Light speed crosses the distance. Light speed does not solve the problem of connection. It does not solve the round trip. It does not solve the communication delay. It does not solve the civilizational fragmentation. It does not outrun the expanding universe. Light speed is a threshold, not a destination. It is the point where the rules change, where the physics of motion enters a new regime. But it is not the point where the problem of cosmic isolation is resolved. That point, if it exists, is farther out, at speeds we cannot yet achieve and do not yet know how to achieve. Knowing this is not a reason for despair, it is a reason for precision, a reason to aim at the right target rather than the wrong one, a reason to ask not how do we reach the speed of light, but what does the universe require, and what is the physics of meeting that requirement? Those questions are hard. They may be the hardest questions physics has ever faced, but hard questions answered precisely have always, in the history of science, led to places that unanswered questions never reached. The universe is large. We are small. The gap between where we are and where we need to be is enormous, and still we look outward, and still we calculate, and still we ask what is possible. But there is a question we have not yet asked directly, and it is perhaps the most personal one in this entire conversation. What would it actually feel like? Not the math, not the civilizational implications, not the governance problem or the communication delay or the cosmic event horizon. The subjective experience of being a human being aboard a ship travelling at a high fraction of the speed of light. What would you see? What would you feel? What would the universe look like from the inside of that journey? Because we have been talking about light speed and near light speed as though they are purely abstract quantities, numbers in equations, constraints on what civilizations can and cannot do. And they are those things. But they are also physical environments, places that a human body would inhabit if human bodies could be brought there. Environments with specific sensory qualities, specific colours of light, specific physical sensations, specific psychological textures. The first thing you would notice at a high fraction of the speed of light is the light itself. As a ship accelerates toward a significant fraction of light speed, the light arriving from ahead of the ship is blue shifted. Its frequency increases, its colour shifts. Stars that were white or yellow or orange at rest appear blue and then violet, and then, at extreme velocities, ultraviolet and beyond. The stars behind the ship are red-shifted. They appear orange, then red, then infrared and invisible. The effect is called aberration combined with Doppler shift, and it transforms the visual appearance of the sky in ways that have no analogue in ordinary human experience. At 50% of light speed, the stars ahead of the ship cluster toward a bright blue ring near the forward direction, compressed by the aberration effect. The stars behind recede and fade. At 90% of light speed, the entire visible sky contracts toward a bright circle directly ahead, surrounded by darkness. The universe appears to be rushing at you from a single point, concentrated, intense, blue, and then violet and then invisible as the frequencies climb out of the visible range. At 99% of light speed, most of the electromagnetic energy from the surrounding universe has been compressed to frequencies far above visible light. The sky appears dark in most directions, with only the forward direction showing anything. And what it shows is not stars, but a brilliant, blinding source of high-energy radiation. The universe's light compressed into a narrow cone directly ahead. This is not beautiful in the way that an ordinary night sky is beautiful. It is extreme, intense, a physical environment that, if you could perceive it directly, would be unlike anything the human visual system was evolved to process. And the radiation arriving from that forward direction would not be harmless light. It would be energetic. At high fractions of light speed, the visible light photons from distant stars and the infrared and ultraviolet photons from other sources are all compressed into higher frequencies. What arrived as radio waves is now microwave. What arrived as microwave is now infrared. What arrived as visible light is now ultraviolet. What arrived as ultraviolet is now X-ray. The ship, at high velocity, is moving through an environment where the entire electromagnetic spectrum has been shifted upward, where the ambient radiation dose from the universe's own background light is substantially higher than at rest. There is a specific threshold worth naming here. At approximately 91.7% of the speed of light, the cosmic microwave background radiation from ahead is shifted to visible light frequencies. The CMB, which is the coldest and most diffuse source of radiation in the universe, has been compressed into something your eyes could see. A faint glow, directly ahead, from the background radiation of the Big Bang itself, now blue shifted into the visible spectrum by the ship's velocity. At higher velocities, the CMB photons from ahead shift further, into ultraviolet, into X-rays, into hard X-rays, into gamma rays. The ship becomes progressively more irradiated simply by moving. not by approaching any particular source of radiation. Simply by moving through the universe at high speed, the ship compresses the universe's background radiation into increasingly energetic forms that deposit dose in crew and instruments and structure at an increasing rate. This is the physical texture of interstellar travel at high velocity, not the cold, empty darkness of science fiction. An increasingly hostile electromagnetic environment, brightening and hardening from the front as speed increases, darkening and redshifting from behind. A universe that appears to compress itself toward a single bright lethal point ahead of you and recede into silence behind you. And here is what makes this texture relevant to everything we have been discussing. The time dilation that makes high-velocity travel attractive, the compression of the crew's subjective journey time, is achievable only at the velocities where this electromagnetic hostility is most extreme. The faster you go to reduce the journey time, the worse the radiation environment becomes. The physics that gives you the subjective experience of a short journey also places you in an increasingly lethal physical environment. You cannot separate the two. They arise from the same relativistic mathematics. Moving faster compresses your time and compresses the electromagnetic spectrum simultaneously. The gift and the cost are the same thing. This creates a ceiling that is not primarily about energy or engineering. It is about survivability. There is some fraction of light speed, probably somewhere between 60 and 90%, where the accumulated radiation dose from the compressed CMB and the interstellar medium becomes lethal for any biological crew on any mission of practical duration. Below that ceiling, biological travel is possible with sufficient shielding. Above it, the universe becomes directly, irreversibly hostile to biological life in a way that no shielding we can conceive of carrying would resolve. And the time dilation, the feature that makes high velocity most attractive from the crew's perspective, is most dramatic precisely above that ceiling. The compression of journey time from years to months to days to hours occurs at velocities where the radiation environment is fatal. The velocities that would make biological interstellar travel subjectively manageable are the velocities that would kill the biological travelers. This is the cruelest feature of the relativistic regime. The universe gives with one hand and takes with the other. It offers time compression and delivers radiation poisoning. It shortens the journey for the crew and lengthens the survival time of the crew in inverse proportion. There is a thought that follows from this. If biological life cannot survive the radiation environment of extreme relativistic travel, then perhaps the ships that cross the galaxy at high fractions of light speed will not carry biological life. They will carry machines, artificial minds, systems that do not require biological tissue to function, and therefore do not accumulate radiation damage in the way that biological tissue does. This is not a new idea. It has been explored in the context of interstellar probes, in the context of uploaded consciousness, in the context of AI systems advanced enough to be considered minds rather than merely tools. The observation that the interstellar environment at high velocity is hostile to biology, but potentially not hostile to electronics, or to some other substrate for mind that is more radiation-tolerant than carbon-based life, is a recurring theme in serious discussions of interstellar travel. But it raises a question that is at the same time deeply practical and deeply philosophical. If the ships that cross the galaxy carry artificial minds rather than biological ones, in what sense is this a human civilization crossing the galaxy? What is the relationship between the artificial minds that survived the journey and the biological beings who built the ships and designed the minds and sent them on their way? These questions do not have obvious answers. They depend on what you think mind is, what you think identity is, what continuity of self requires. They are among the deepest questions in philosophy, and they have not been resolved even in the context of ordinary human experience, let alone in the context of minds uploaded to radiation-tolerant substrates and launched across the galaxy. But they are questions that the physics forces us to take seriously, because if biology cannot cross the interstellar distances at the required velocities, and if the alternative is some form of mind that can, then the future of intelligence in the universe may look very different from the future of biological humanity in the universe. Those two things may not be the same. There is one more dimension of the light speed problem that has not yet been explicitly addressed, and it concerns not the galaxy or the universe at large, but our immediate cosmic neighborhood, the planetary system of our nearest stellar neighbor, and what we actually know about it. Proxima Centauri, 4.24 light-years away, is a red dwarf star. It is small and dim by stellar standards, only about 12% of the Sun's mass and about 0.15% of the Sun's luminosity. It is old. Red dwarf stars of this type are thought to be among the longest-lived objects in the universe, potentially burning hydrogen for trillions of years. In stellar terms, Proxima Centauri is hardly middle-aged. In 2016, astronomers confirmed the existence of a planet orbiting Proxima Centauri in its habitable zone. The planet is called Proxima b. It has a minimum mass of about 1.07 Earth masses, indicating it is likely a rocky planet rather than a gas giant. It orbits its star at a distance of about 7.5 million kilometers, completing one orbit every 11.2 days. Because Proxima Centauri is so dim, the habitable zone, the range of distances where liquid water could exist on a surface, is much closer to the star than Earth is to the Sun. Proxima b may be within that habitable zone. It may have liquid water, it may have an atmosphere, we do not know. What we know is that it exists, that it has approximately the right mass, and that it orbits at approximately the right distance. We also know some things that are less encouraging. Proxima Centauri is a flare star. It produces powerful and frequent stellar flares, bursts of energetic radiation that can be hundreds of times more energetic than typical solar flares from our own Sun. These flares bombard Proxima b with ultraviolet and X-ray radiation at intensities that would be lethal at the surface of any unshielded world. Whether Proxima b has a magnetosphere strong enough to deflect this radiation, or an atmosphere thick enough to absorb it, is unknown. Proxima b is also almost certainly tidally locked to its star. At such a close orbital distance, the gravitational interaction between the planet and the star is strong enough to slow the planet's rotation until one side permanently faces the star and the other side permanently faces away. The day side of Proxima b receives constant illumination, with temperatures potentially hot enough to be hostile to life as we know it. The night side is in permanent darkness, potentially cold enough to freeze any atmosphere it has. The habitable region, if any exists, might be a narrow band around the terminator, the boundary between the permanent day and the permanent night, where temperatures could be moderate. This is not the picture of a comfortable habitable world, but it's also not the picture of a definitively uninhabitable one. Environments that would kill an unprotected human can, in principle, host life that evolved in them. The deep-sea hydrothermal vents on Earth, where temperatures exceed the boiling point of water and pressures would crush an unprotected human, host complex ecosystems of organisms that evolved in exactly those conditions. Life has a way of finding niches that seem hostile by the standards of the surface conditions in which most life on Earth evolved. Whether life found a niche on Proxima b is one of the most important unanswered questions in science. It is a question that, with current technology and current telescopes, we cannot answer. We can model the stellar flare environment. We can estimate the probability of an atmosphere surviving for geological timescales. We can calculate the tidal locking conditions. We cannot directly observe the surface of Proxima b or the composition of its atmosphere with any current instrument at the required precision. We could answer it by going there, or by sending something there. A probe at 20% of light speed, arriving in roughly 21 years, doing a brief flyby and transmitting images and atmospheric spectroscopy data back to Earth, would give us the first direct measurement of a planet around another star, the first pixels of another world, the first atmospheric chemistry from beyond our solar system. That mission is what Breakthrough Starshot is attempting to design. Not a crude mission. A gram-scale sail, accelerated by a laser to a fifth of light speed, crossing to Proxima Centauri in about 21 years, transmitting data for 4.3 years in transit, with the first results arriving at Earth approximately 25 years after launch. At that scale, light speed is fast enough. A 25-year timeline for first results is within human institutional memory. The researchers who design and launch the mission can realistically expect to be alive when the first data arrives. The civilization that funded the mission is the civilization that receives its results. But this only works because Proxima Centauri is so close. 4.24 light-years, the nearest star, the minimum possible interstellar distance from Earth. At this distance, and only at this distance, light-speed communication and near-light-speed probe transit combine to produce a mission timeline that fits within human experience. Anywhere else, the math breaks in the ways we have spent this entire conversation describing. Anywhere beyond a handful of the very nearest stars, the round-trip time exceeds anything that institutions can sustain, anything that human memory can hold, Anything that makes the mission meaningful to the civilization that launched it rather than a message in a bottle. The nearest star is just barely reachable. Everything else, by any metric of meaningful human exploration, is not. And that is the honest summary of everything we have discussed tonight. The universe is large. Light speed is real. Even light speed is not enough. The gap between what we can achieve and what we would need to achieve to explore the cosmos in any meaningful sense is enormous. Not a gap that imagination or ambition or determination can close. A gap that only physics can close, and only if the physics, in some regime we have not yet discovered, turns out to be more permissive than our current understanding suggests. We do not know if it is. We are working to find out. The investigation is ongoing, serious, and not yet complete. That is where we are. That is what we know. And knowing it precisely is the beginning of everything that comes next. Strap in, keep looking outward, and stay with the crew. If you want more mission briefings like this, subscribe for the next journey.